We've understood that. The third and last operation, which is even simpler, is called find. All you do with find is you walk down the S list, and you just keep checking to see if what you're trying to find you walk down the S list and see if the item that you passed in as your parameter is equal to the object of the head of the node that you're pointing at as you walk down. If yes, if it's there, then return true. And if you reach the end, if you reach the end of the list, then return false, meaning it's not there. That's it with find. So now we can start talking about the runtimes of the SList operations. So we talked about insert, front. Insert front, we have to talk about its worst case and its best case scenarios. However, luckily for us, there really isn't a worst case or a best case scenario. There's only one case because we're only removing the front node. And all that's happening there is we create a new node and then we rearrange pointers. Those are all constant primitive operations. Actually, to be specific, you're really making only 3 operations. So as a result, the runtime is constant. So then we talk about insert end. Insert end is walks to the end of the list, creates a new node, and then rearranges pointers. The creating a new node and rearranging pointers is 3 operations. Fine, that's simple. However, what is really important is that the act of walking down the list takes n operations, because you have to walk down all the way to the end. This happens no matter what case it is. So that's n operations, because you're calling head equals head.next n times as you iterate through the list. So this ends up being big O of n time, no matter what. The same logic applies to remove front and remove end. Remove front just rearranges pointers, so it's in constant time. And remove end walks down to the end of the list and rearranges pointers, so it's in big O of n. This happens no matter what. Find, on the other hand, has a worst case and a best case scenario. The worst case scenario is if you have to walk down, if the item that you're looking for is at the end of the list, in which case it's in big O of n time, because you have to walk through the entire list, then you reach the end, and then you realize, okay, they're there. Or if it's not there. Either way, if it's not in the list, then you have to walk through the whole list anyways to check. Best case scenario is if the first node, the head node, contains an item that's equal to the target, in which case it's a constant time operation, because you just check the first one and you're done. So that's all you have. That's the runtimes of the singularly linked list data structure. However, one thing to finally notice is that it seems weird that we have to work with linear time operations for insert end and remove end. I wonder if there's a way to make it work in constant time. And you're probably noticing that there is, because the way we made this constant and this constant was that we had a head pointer pointing at the front of the list. Well, what if we had a tail pointer that pointed to the last item of the list, and that we constantly maintained in every single method? So the way we do that would look like the following. Let's say we have the following SList. 4 items, and they contain some item. I'm not going to show them, just to be quick. Head would point here, and just like that, we would also maintain a tail that points to the last item of the list. This way, when we want to do insert end or remove end, we don't have to call the head, we can just call the tail. Because they're two, instead of one thing pointing to this node, which was this, and which was this, there's also another thing pointing at this node, which is the tail. And so all we have to do is rearrange the pointers with that reference the tail, as opposed to referencing the head. And that's it. As a result, you can make both remove end, and insert end in constant time. So that's a great way to augment data structures. You should always be thinking of ways to augment your data structures to make them better. And this is one example of which we can do that. Next time we'll be talking about doubly linked list, with which optimize find as well. Well, ideally would optimize find. So the final thing we're going to be talking about is working through a popular interview question, which utilizes linked lists. So here's the problem. Let's assume you have a linked list, but let's assume that you weren't implementing the size field and you don't know how big your list is. And so you have the following list. And they're storing items, I just haven't included them in the illustration. Okay? So we want to find out exactly where the median of this, what the median of this SList is. And actually I'm just going to add one more to make life easier, to make it easier to see. So disregard this X. Sorry. So the first thing we do is we create a pointer, 2 pointers. We say pointer 1 points to head, and let's say this is head. And pointer 2 points to head.next. What we want to do is we want to increment pointer 1 so that it moves down 2. So that it moves down, so it increments down 2 nodes. So now it's pointing here. So it's pointing at every other node. And then we check to see if pointer 1 is at the penultimate or the final node. If it's not, then we advance P2 by 1 node. And we keep doing that. So then what will happen is we get rid of this, and then we advance P1 to this node. Notice that's not at the penultimate node. So then we advance P2 here. Oops, sorry. My bad. We advance P2 here. Okay, so P2 is finally here. And then we notice, then we move it down to the next, then we advance it down 2 nodes, right? And then when we're done with, and now we reach the final node, and so we advance this one more, and we're here. And so now we're here, and you realize, oh, we're at the final node, so we can't advance this anymore. So we just return the value at the median node, which is right here. And notice, however, that it just so happens that we reach the median node. And so that's how this problem works. You're advancing P1 and P2 down at a certain rate, so that way you reach the middle of the node. And so that's a very popular question, and that's how you reach the median towards the end. So I hope that helps. And while this was long, I think it's extremely necessary to make sure that you're totally clear about the SList, so that way when we move forward, we can use the SList to implement many other data structures, such as trees, heaps, so on and so forth.